हेलो। या व्हाट आई एम सेइंग कि पिछली क्लास में हम डिटरमिनेंट मैट्रिक्स को प्रैक्टिस कर रहे थे, याद है? हेलो। एम आई ऑडिबल?
Yes, sir.
So what I was saying, in the last class also we have been practicing determinant matrices. So today also we'll do few more questions over it. Let's start with question number 61 first. Very good question, very well defined. बहुत सोचो सोचो इसके बारे में कि मुझे क्या करना चाहिए, एंड गिव मी ए थॉट आल्सो क्विकली. Any idea anybody would like to suggest? देखो एक चीज सोचो. Think of something what they are saying in the question. The number of 2 by 2 matrices A whose entries are 0 or 1, for which the system has at least two solutions. Let us assume that the matrix we are talking about is A, B, C, D. Now A, B, C, D multiplied by X and Y, and what do you get? You are getting 0, 0. That means AX plus BY is 0 and CX plus DY is 0. Yes or no? Tell me. Now, if you realize, these are two linear equations. So, two linear equations, either they will intersect at one point and will have a unique solution, or they will be completely overlapping, and in that case, they will be having directly infinite number of solutions. Am I correct? Up questions may also, in this question they are saying system has at least two solutions. At least two solutions. That means there is no case of two solutions, three solutions, four solutions. This is directly a case of infinite number of solutions. All right. So this is directly a case of infinite number of solutions. Infinite number of solutions. And now for infinite number of solutions, what do they expect you? These two should be overlapping. Means A upon C should be equal to B upon D. That means AD equal to BC. That means determinant of A should be what? 0. Am I correct? Now the question is number of 2 by 2 matrices made with 0 or 1. So that the system is having infinite number of solutions. Now think of something, determinant. How can you make determinant A 0? If your A is like this, two zeros, two ones, or two zeros, two ones, or two zeros, two ones, or two ones, two zeros. One of few of the four cases. All right. After that, see, also using two zeros, two ones, you cannot use this kind of case because in this way, determinant of A is not getting zero. Now, anyhow, if I use three zeros and one, determinant will definitely be going to zero. Now, this they can be made in four ways. Now, if there are all four zeros, value of determinant definitely zero. If there are all four ones, value of determinant definitely going to be zero. So I have done, okay, another case, if there is only one zero. Now, anyhow you arrange them, you will never get determinant value zero. Anyhow you arrange them. Got it? So this is also cancelled. So what is the answer going to be? 4, 4 here, 8, 1, 9 and 1, 10. So there will be total 10 such kind of matrices A. Am I correct? Did you understand everybody? Tell me, am I correct?
Yes, sir.
Now, try with 62. 62. क्या करोगे? नहीं मिलेगा. Yes, Vijay, you are such a smart boy. Keep your camera on. Vijay, where do you belong to? Who is this Captain Jake Sparrow? Yes, 62. If determinant of B is 1, find the number of values of alpha in minus 2 pi to 2 pi. Yes. A is cos alpha, sin alpha, minus sin alpha, cos alpha. B is defined as this. See, there are two catch. On the one hand, I can say that this B look like I plus A to the power 5. If I take A common, 4C1, 4C, I plus A to the power 4 into A. Before that, do one thing. Like, this is not correct. Do one thing. Definitely, they are not asking ki you do A cube, A ki power 4. So, best, first of all, we do A square. Fine. So, if I do A square into it, cos alpha, sin alpha, this is your A. So if you do a square, that is cos alpha, sin alpha, minus sin alpha, cos alpha, multiplied by cos alpha, sin alpha, minus sin alpha, cos alpha. What do you get? First row, first column, cos square alpha minus sin square alpha. That is cos 2 alpha. First row, second column, sin alpha cos alpha plus sin alpha cos alpha sin 2 alpha. Second row, first column, minus of sin 2 alpha. Second row, second column is again cos 2 alpha. That means this is for sure. If you try to calculate a cube here, what are you going to get? Cos 3 alpha, sin 3 alpha, minus of sin 3 alpha, and cos 3 alpha, and so on so forth. This is what the pattern is going to get followed. All right. Now they are asking for determinant of b. Now see, this b is given to you a plus 4a square, 6a cube, 4a to the power 4 plus a to the power 5. If you take a common, it is I plus a to the power 4. Am I correct? So that means determinant of p is determinant of a into determinant of I plus a to the power 4, which is given to me as 1. Also, determinant of a is very much clear to me. It is 1. That means I plus a determinant to the power 4 is also 1. Am I correct? I plus a determinant to the power 4 is also going to be 1. Now, if I try to find I plus a, it is 1 plus cos alpha, sin alpha, minus sin alpha into 1 plus cos alpha determinant. This should be equal to plus minus 1. So it is 1 plus cos alpha whole square plus sin square alpha. It should be plus minus 1. Fair enough? So if you expand this, what do you get? Sin square alpha plus cos square alpha plus 2 sin alpha, 2 cos alpha plus 1. It is either 1 or it is minus 1. That means this is also 1. So 2 times 1 plus cos alpha is going to be 1 or minus 1. Am I correct? So cos alpha plus 1 is going to be 1 by 2 or minus 1 by 2. Means cos alpha is going to be minus 1 by 2 or minus of 3 by 2. Now, cos alpha can never be minus 3 by 2. That means cos alpha is minus 1 by 2. So, how many ways cos alpha gets minus 1 by 2? There are two values. One is first, second quadrant and third quadrant. So, alpha is going to be pi minus pi by 3 or pi plus pi by 3. So, your answers are 2 pi by 3 and 4 pi by 3. This is your answer. Am I clear? Now see, initially I tried to find a square, a cube, but it did not result into anything in this case. So it happens. Like you try a method, you don't get any particular result from that. So that does not mean that you have tried something useless. See, but in further questions, this thing may help. Like if you have this kind of matrix, their a square is going to be double angle, a cube is going to be triple angle, a to the power 4 is going to be fourth angle, and so on. So this knowledge, it did not result anything here, but it may give you certain better results in future questions also. Am I correct? Ranju, understood?
Yes, sir.
Gautami, have I made it clear? All right. Let's go next. Very good question it was, 62. Now question number 63. A very good example of symmetric matrix or how to make symmetric matrix. Yes. 63. Find the number of all possible symmetric matrices of order 3 by 3 with entries -1, 0, 1 and whose trace is equal to 1. Now, I hope you remember what is trace. Yes or no? Now, number of all the possible symmetric matrices of order 3 by 3 with these entries. Now see, this is question number 63. Since you are trying to make a symmetric matrix, let the diagonal entries be A, B, C. So they are saying A plus B plus C is 1. How can you make A plus B plus C 1? With -1, 0 and 1. One way is you keep two zeros and one 1. Other way is you keep a -1, a 1 and another 1. That's it. These are the only two ways in which you can make sum of AB, these three entries as 1. Now, in how many ways these three entries can be placed at ABC? Three ways. And in how many ways these three entries can be placed in ABC? Again, three ways. So there are total 6 ways to design the diagonal matrix. To design the diagonal, I would say. Now, after designing the diagonal, P, Q, R, you have to decide. Lower triangle is itself going to have values as P, Q, R. Why so? Because lower triangle in itself is going to have values as P, Q, R because it is a symmetric matrix. Now, P entry or Q entry or entry, each one can be filled in three ways. Either you put it 1, -1 or 0. And whatever you put, the same will come at lower triangle. Now, P can be filled in three ways, Q can be filled in three ways, R can be filled in three ways. That means required number of matrices is 6 into 3 into 3 into 3. That is 81 into 2. 81 into 2 is 162. This much number of symmetric matrix you can construct. Am I clear? Is it okay, everybody? Now, go with question number 64. Let A equals to Aij be a 3 by 3 matrix. If A plus A transpose is this, where A12, A23, A31, A12, A23, A31 are the positive roots of this equation, find the value of determinant of A. Very good question. Very amazing. Give it a try. Question number 64, quickly. Yes, quickly. Right. See, A equals to Aij be a 3 by 3 matrix if A plus A transpose is this. With this information, they are just trying to say that this matrix, this is a skew symmetric matrix. That is very much clear. So what they're trying to say, A21 plus A12 is 4, A31 plus A13 is also 4, and A23 plus A32 is also 4. Correct? Then they are saying A12, A23, A31 are positive roots of this equation. Now there is a very good thing about this equation. See, equation you have x cube minus 6x square plus px minus 8 equal to 0. Now they are saying roots of this equation are A12, A23, A31. Yes or no? If I ask you to find the sum of roots A12 plus A23 plus A31, it is 6. If I ask you to find the product of roots A12 plus A23 plus A31, this is going to be 8. Now, can you tell me A12 plus A23 plus A31 by 2? It is going to be 2. Sorry, I made a mistake. This is multiplication. A12 into A23 into A31. This is 6, 8. So, A12 into A23 into A31 raised to the power 1 by 3 is also going to be 2. Did somebody got a hint? This is what? Arithmetic mean of A12, A23, A31. And this is what? Geometric mean of A12, A23 and A31. And whenever arithmetic mean is equals to geometric mean, that means that means quantities at which AM and GM is applied are equal. Am I correct? So the quantities at which AM and GM is applied are equal. That means A12 is equals to A23 is equals to A31 is equals to 2. Correct? Now the question is, find the value of determinant of A. Now, A12 plus A21. Now, this is what? This is twice of A11. This is twice of A22. And this is twice of A33. That means A11 is 3, A22 is 5, A33 is 4. Now let us design the matrix A. This is going to be 4. This is going to be 3, 5, 4. Now, A12 is 2. A23 is also 2. A31 is also 2. Now A31 plus A13 is given to me as 4. So A31 is 4. So that means A13 is also 2. Well, sorry, A31 is 2. So A13 is also 2. So rest all the entries are going to be. Now they are asking for determinant of A. I think this is what you can calculate. Yes or no? Determinant of A आ जाएगा. Everybody understood? Latika? Now, nobody is ready to speak. Go with this question. Let A be a 3 by 3 matrix given by A is Aij, B is a column vector such that B transpose AB is a null matrix for every column vector B. C is A minus A transpose and A13, A23, A3, A21 is given. Find the value of determinant of adjoint A plus determinant of adjoint C. Yes, do it. Quickly try. A be a 3 by 3 matrix. So let's do it. A be a 3 by 3 matrix given by this. P is a column vector such that this. Now see. A be a 3 by 3 matrix. This is question number 65. Let us assume A is A11, A12, A13, A21, A22, A23, A31, A32, A33. Let us assume B is a column vector they are saying. Let us assume this is X, Y, Z. Yes. Now, according to them, B transpose AB. Now see, order of B transpose is 1 is to 3. Order of A is 3 is to 3. And order of B is 3 is to 1. That means this entire product is going to be of order 1 is to 1. Single element. And in the question, they are saying that this is a null matrix. That means whatever the product will come out, it is going to be a null matrix, means single element is 0. Now, little bit of efforts we have to do. Let it is X, Y, Z. Then this entire A has to be here. Then again a column vector X, Y, Z, and it has to be 0. Now, what this product is going to be? First row, first column, X times A11, Y times A21, Z times A31. Then first row, second column, X times A12, Y times A22, Z times A32. First row, third column, X times A13, Y times A23, Z times A33. Then you multiply it again by X, Y, Z, and it is going to be a null matrix. Correct? Am I correct? Now, multiply it further. So finally, the single element that you are going to be one row, one column only. That is x square times A11 plus xy times A21 plus xz times A31 plus xy times A12 plus y square times A22 plus yz times A32 plus xz times A13 plus yz times A23 plus z square times A33. And this has to be null matrix, means the quantity inside should be same. So they both are going to be 0. Now if you realize it is A11 into x square plus A22 into y square plus A33 into z square plus what is there with xy? With xy, you have A21 plus xy A12. With yz, what do you have? Yz A32 plus A23. And with zx, what do you have? Zx A31 plus A13. And this is going to be 0. Now, there is a catch in the problem. In the problem, they are saying that for every column vector B, means this equation, this latest equation which I have written, it is valid across x, y, z. If it is valid for every x, y, z, that means it is an identity in x, y, z. If it is an identity in x, y, z, that means coefficient of x square, y square, z square, xy, yz, zx, every coefficient should be 0. That means A11 should be 0, A22 should be 0, A33 should be 0, then A21 plus A12 should be 0, then A32 plus A23 should be 0, then A31 plus A13 should be 0. Yes or no? And now, if they all are going to be 0, that means A is a, that means A is a skew symmetric matrix. Skew symmetric matrix. A is a skew symmetric matrix. Now what they are asking? So A is a skew symmetric matrix. That means determinant of A is going to be 0. Now C again. This C is quite clear. It is also in skew symmetric matrix. So A is a skew symmetric matrix and C, that is A minus A transpose, is also a skew symmetric matrix. So if they both are skew symmetric matrix, that means determinant of A is 0 and determinant of C is also 0. They are odd order skew symmetric matrix. So their determinants are going to be 0. Now they are asking you for determinant of adjoint of A. That is determinant of A square, that is also going to be 0. And determinant of adjoint C, that is determinant of C square, that is also 0. So the answer of your question is going to be 0. Have a look. Yes, yes, quickly. Now, question number 66. Give it a try. If T is real and lambda is this, then find the number of solutions of the system of equation this for a particular value of lambda. T is real and lambda is this. Yes. Quickly try. First of all, get the values of lambda. Or directly values we won't be able to get the system of values of lambda. See, what they're saying, lambda is 3t square. Lambda is what? T square minus 3t plus 4 upon t square plus 3t plus 4. Lambda is what? T square minus 3t plus 4 upon t square plus 3t plus 4. So first of all, let us find out for real t what can be the values of lambda. So let's cross multiply. So it is lambda t square plus 3t lambda plus 4 lambda is t square minus 3t plus 4. Correct? So it is lambda minus 1 t square plus thrice of t plus 1, thrice of lambda plus 1 into t plus 4 times lambda minus 1 is going to be 0. Now, for real t, its d should be more than or equal to 0. D more than or equal to 0 means 9 times lambda plus 1 whole square minus 16 times lambda minus 1 whole square. It should be more than or equal to 0. Let us write it. Just a moment. So let us write it 3 lambda plus 3 whole square minus 4 lambda minus 4 whole square more than or equal to 0. Apply a square minus b square. Got it? Now apply a square minus b square. So it will be a plus b, that is 7 lambda minus 1, a minus b minus lambda a plus 1 minus lambda plus 7 more than or equal to 0. So it is 7 lambda minus 1 into lambda minus 7 less than or equal to 0. So your lambda lies between 1 by 7 to 7. So lambda lies between 1 by 7 to 7. Now the question is, for t is real, the system of equations, this for a particular value of lambda. So first of all, what we do, let's try d. If I try d is going to be determinant 3 minus 1 4, 1 2 minus 3 and 6 5 lambda. So if I try to calculate it, it is 6 times 3 minus 8 minus 5 minus 5 times minus 9 minus 4 minus 13 plus lambda times 6 plus 1 7. So it is 7 lambda minus minus plus 65 minus 30. So it is 7 lambda plus 35. That is 7 times lambda plus 5. So for these values of lambda, this determinant is never 0. Determinant is 0 when lambda is going to be 5. That means for these values of lambda, this determinant is never 0. And if this determinant is never 0, you are always going to get unique solution. Got it? They're asking for the number of solutions. So the number of solution is going to be unique solution. That means number is 1. One solution you are going to get. Whatever the solution is, we have no issue with that. We have no business with that. We don't have to calculate that. Now, go with question number 67. Let A, AI, J be a... Anybody having any particular doubt for 65, 66? Anyone? Anybody who would like to ask something from 65, 66? Very good. Now 67. Let A is Aij be a square matrix of order 2, where Aij belongs to 0, 1, 2, 3, 4, 6. Find the number of matrices A with distinct elements such that A into A inverse is I. Now see, A into A inverse I means A inverse is existing. A inverse will exist if determinant of A is non-zero. All right. So what simply you have to do, you have to find the number of 2 by 2 matrices for which their determinant is not going to be 0. Am I clear? Because A into A inverse equals to I, this will happen for every matrix. If it is invertible, this will happen for any matrix. Now the only condition that we are left with, is it invertible? And if it is invertible, its determinant should be non-zero. Tanush, understood? Tanush,
Yes, sir.
did you find today's question quite insightful? Dhruv, Chandrika, see, that is the problem with your batch. You guys don't speak up. If you won't speak up, how would I feel like? You feel like you are talking to walls. You just switch on your computer, you sit in any meeting, you 10 times you go, 10 times again you come, but whatever is happening, you have no idea. You don't ask anything, you don't talk to any educator, I think. What's happening? Anyways, I leave this question for your perusal. Write down the question, do it on your own. Very good question it is. And tomorrow again, we will practice few more questions from this particular chapter. Then day after tomorrow, Wednesday onwards, we will start with relations. The very first chapter of 12th NCRT, relations. All right. All right. That is all from my side for today. Thank you so much.